Thanks for coming to the session. My name is Tarek Matkour. I am the Group Program Manager for the Visual C++ team at Microsoft. So we create the Visual C++ product, the compilers, the libraries, the IDE, IntelliSense, all good parts of it. I'll be talking to you today about how to create fast applications for Windows 8. One of the reasons we ask our developers, why do you use C++? And 3 reasons come up top all the time. First reason is performance. We use C++ because we really want our apps to be fast. The second reason is portability. We care about our apps working across multiple platforms, working across multiple devices. We want to be able to take the same code and run it everywhere. And the last reason, and also a very, very important reason, is compatibility. I already have libraries that I want to use that I want to be compatible with. I already have existing source code that I want to use that I want to be compatible with. Multiple reasons for compatibility. So today we'll focus on the first one, on performance, and how you can use C++ to create highly performant Windows 8 applications. So I'll touch a little bit on Windows 8, but most of my focus is going to be about performance and how can you create the fastest applications possible. So I'll spend a little time just to give a brief overview of why Windows 8, why it's important to create fast applications for Windows 8 as well. And what is it about Windows 8 and the form factors that we target that make performance essential and make C++ even more important. And then I'll talk a little bit about some of the things that you get for free just by being a C++ developer in terms of performance. Then we'll talk a little bit about how you can get the maximum out of the hardware that you have. That's one of the things about using C++ is that you're very close to the hardware. So how can you get the maximum out of the CPU, get the maximum out of the GPU, and how does that work? So we'll be talking about those, and we'll be giving a couple of demos. Who's a C++ developer? Almost everyone, okay? And who's already creating Windows 8 applications? 1. All right. Who's interested in creating Windows 8 applications? Most. Okay, great. So we'll talk to you a little bit about Windows 8 and what it means, okay, from a C++ perspective. When you think about Windows 8, there are a number of things that come to mind that make it different. Who's already creating a desktop application? Who's creating a web application? Mostly in the desktop world. So I'll talk, about the differences between the Windows 8 world and the desktop world. Well, first of all, Windows 8 has a desktop, right? So it continues to have everything that you're already used to programming. But one of the things that we added for Windows 8 is the concept of Windows 8 Store applications. And what is different from desktop applications about those Windows 8 Store applications? Number one is they're geared towards machines that look like this, things that you carry in your lap, you sit on a couch, you're interacting with your fingers. Whereas, on a desktop, you can really assume there's a keyboard, there's a mouse. On this machine, you might have some kind of keyboard, maybe like an on-screen keyboard, something a little bit better than an on-screen keyboard, never like a really nice keyboard that's comfortable. So you can't rely that a user has those kinds of devices. Definitely a mouse is almost a non-option in most scenarios for these kinds of tablet machines. Very touch-friendly, so you expect this high interactivity. The other thing is the concept of trust. How many of you, when I go to back to visit my family, typically I act as the IT guy for the family. Who does that for their family? Okay, all of you. So you understand, you can relate to what I'm talking about. One of my biggest problems when I go back home is, I'd sit on my, my mom's laptop or my father-in-law's laptop, and the first thing I start doing is uninstalling all the applications that they've installed since I last visited them. And I tell them, why are you installing? Why are you installing all these applications? And they ask me, what does installing mean? I just clicked stuff. These things just come on my laptop. Well, we don't want that kind of experience for Windows 8. So one of the things that was important when creating the concept of Windows 8 Store applications is it is very clear when you're acquiring an application, those applications are not going to affect any other applications on your system, and you cannot randomly get an application. You can't just browse the website and get an application. You have to go to the store, have already been authenticated with that store, get something that you will see reviews on and be trusted. So that concept of trust is very important. And then finally, because you're getting those things on a mobile machine, battery power is very important, right? You don't want the person who is going to be using your application to go give it a 1 star, because every time they fire your application, it goes and takes 3 hours before the next charge, whereas normally it takes them 7 or 8, right? You don't want your application to be the one killing the battery. Also, because you're using a smaller device, usability studies actually say that it is more important to be interactive and fast with these applications than a desktop application. When you have a keyboard and a mouse between you and the machine, there is an expectation that you're dealing with something that is not instantaneous. But when you're dealing with a real-life object, it's just like moving this. Your expectation is that you're going to move it, and it's going to react with you. It's going to move with you. Similarly, when the machine is so close and you're moving things with your hands, research studies say you actually expect it to be more performant. Now, this puts you as a developer in a very hard position, because the machine is less powerful, yet people expect it to be more performant. So what do you do as a developer? So that's one of the reasons why I'll focus on the last 2 parts of it. For us in C++, this is where you excel with C++ applications. Some of the videos that you saw while you were waiting were talking about people creating some of those very interesting applications and games and the little reading app and all of that. And they were using DirectX and they were using C++. And many of the reasons they were doing that was they wanted that very nice performance. You click on the word fish, and the text animates, and it moves to the other side, and everything is performant. There's no jittery. You get the 45 or 60 frames per second that you want. So I'll focus today on the battery power and the performance aspect of a Windows 8 Store application. As a C++ developer, you have a number of ways to create those applications, and I will not go deep. This is just the only slide I'll really have about this. So if you want to learn more about it, you can come talk to me, and I'll give you some pointers on where to learn more about them. But you can create with C++ XAML-based applications. So anybody using WPF or Silverlight already? More than half, okay. And basically the same XAML that you have for WPF and Silverlight. XAML is a declarative framework for UI. And it's a very easy to use with very nice designers and drag and drop. It's a very, very nice experience. And you can use that directly with C++. You can also create a DirectX application. And if anybody using DirectX already? Only one, okay? If you're already using DirectX, it is exactly the same DirectX that you've been using forever, right? And you're able to use that in Windows 8 Store applications. You can create hybrids of XAML and DirectX. You can have a DirectX surface on a big XAML application that has the controls in XAML, and then like the animation and the really cool, fast and fluid stuff is done in DirectX. Or you can create a JavaScript application and just use C++. And you can use C++ as a way to power the very performance-sensitive aspects of your application. So there are many places to use C++ in Windows 8 applications. And the choice of which one is really up to you. But there is a place when you really need the power and performance to be able to find C++ and use it there. One of the really nice applications that I always like to demo to sort of give the what's possible with C++ and Windows Store applications is FreshPaint. So let me show you what that looks like. Who has seen FreshPaint before? Only a couple, okay. So FreshPaint is an application on the Windows 8 Store. You can go on the Windows 8 Store and download that application. It's free. It's developed by some of our teams in Microsoft. And it was created as a demo for, here's how you can create a very nice app. Here's what's actually possible. FreshPaint, you're not able to see it, huh? Is there a reason it's not showing the screen? Sorry, I'm trying to show you my screen. It's not coming up.
Yes, duplicate.
Okay. Thank you. This is better. Good. All right. So FreshPaint is one of the applications you can get on the App Store, on the Windows Store. And I'll click that and start it. And it's basically a drawing application. You use your fingers. You can actually even use brushes or a stylus pen or whatever it is that you want to use. And you can create drawings like this. And the nice thing about it is, here you have your canvas that you can paint in. You have different kinds of utility brushes, pencils, chalks, a paint palette that you can choose from. You can select chalk, and then it will give you the palette for the chalk, or you can select, a white brush or a smaller brush. I can select a color, put it here, maybe mix it a little bit with yellow, and as I mix it, see how it drags a little bit of the color with it. Now I go to the canvas, and I start drawing on the canvas, and you see how, the edges of it really mimic what happens on a real canvas on paper. I can select different kinds of paper, and if I change the different kinds of paper, the interactivity of how the pen actually goes with the paper is going to be different. I can choose colors. Oh, sorry. Let's say it's a nice pink color. I move that, and I mix it with green, and you see on the paper, there's the same kind of mixing that happens. You can let it dry, and then when you're coloring, it doesn't mix anymore. You can do all these kinds of interesting effects. And to be able to do that very smoothly, you really need strong performance. And that's why that team selected C++ to implement this. Just a word about how this was done. See that whole canvas that we have here? This is DirectX. DirectX controls the brushes. DirectX controls what's on the screen. You get very deep control over the actual drawing area. But when it comes to showing this kind of UI on the top, or the buttons on the bottom, there's no need to reinvent the wheel and kind of like redraw what a circle button looks like. These are all things that you can do easily with XAML. In fact, the top control that you see here was actually done with a designer, with the designer in Visual Studio. In the File New project, you get the designer and you drag and drop stuff. This was done with that. So this is 100% XAML on the top, and the actual drawing surface is DirectX. And the whole app is a combination of XAML and DirectX written all in C++. So that's what you can do in terms of getting a very fast and fluid Windows 8 application. And then I'll talk to you about how you can create some of those things in C++. All right? Now let's see if I can get back to my screen here. Now, let's go back to the normal view. Good. Okay. We'll skip ahead again. Sorry about that. All right. So let's start talking about different ways to improve the performance of your C++ applications. Well, number one, just by using C++, you get a number of free things. C++ compared to any of the other languages that you have, C++ is compiled all at your design time. While you're building your app, you actually get to compile it, and you get to generate a binary. And that binary contains all the machine instructions that are actually going to run on the user's machine. There is no code generation that happens on the user machine. Now, there is a benefit to that, and there's a drawback to that. If you compare it, for example, to C# or JavaScript, much of the code generation happens on the user's machine. There's a JIT, and the JIT is the one that actually generates the code. There's some kind of intermediate code generation that happens on your developer machine, but most of the code generation actually happens on the user machine. The benefit of having the generation of the code happen on your machine as a developer is that you can take all the time that you want to create the most optimized application. As a compiler has all the time in the world. It can spend, if you let it spend all the time, and as a C++ developer, you already know our compiler takes its time, right? And one of the reasons it takes its time is it's actually trying to create a very good code, especially on a release build. You don't have that luxury if you're using a JIT. You don't want the user waiting for the JIT to create really fast code, but they've already been waiting. That's already taking from the user time. So it's a very hard trade-off that the JIT has to make. None of this happens in C++. On your machine, we're going to create the most optimized code. So what kind of optimizations do we do? Well, the first and the most important, and the one that almost everybody uses, is what we call compilation unit-based optimizations. This is the, when you throw the /O2 or O1 switch on your project. And from our telemetry data, we get telemetry about what people use when you say, yes, please participate in the customer experience product with Microsoft, which about 15% of our customers do. We get data about what switches they throw so that we know where to invest and what to start talking to people about if they don't use it. So one of the things that we know almost everybody does is throw that O2 switch. How does O2 work? It's a quick recap. It's always happened. You have your CPP files. You invoke the compiler on them. We create OBJs. Those OBJs are actually optimized. Like they have pretty optimized code in there. We go through another phase of the compiler, and that second phase does a lot of optimizations on a CPP by CPP basis. So the first CPP, we take it, we optimize it as much as we can, we create the OBJ out of that. The second CPP alone, on its own, we optimize it and we create the second OBJ. And at the end, we get a linker and it creates an exe out of it. Now you have an optimized exe. That's the most basic form of optimization. It's existed forever. You all use it. But that's how it works. The next interesting phase of optimization, we call it whole program optimization. And from our telemetry, maybe 60% of our customers use it, but 40% don't. And for those 40%, please go use it because it's free. It's almost free to you. You will spend a little bit of extra time building in your, well, not a little bit, some extra time building in your release build, but you get roughly in the applications that we measure, on average 10%. Just a 10% performance boost on straight line code, normal code. And your mileage will vary, but that's average that we see just by throwing that switch. So just throw GL and LTCG, one on the compiler and one on the linker, and you get a performance boost. Now, how does that work, and why is it different from O2? You have your same CPPs. When you compile them, we're going to create the OBJs, and the OBJs are going to have some optimization in them. And then before we link, we combine those OBJs, and we do further optimization on that combination. So let's say you had one function on one CPP file calling another function from another CPP file. We can say, you know what? That function is always called from the first function, the other CPP. I can inline them. And you can start to do things like inlining source code from one translation unit to another translation unit, which are things that we didn't do with O2 and friends. Right? So now you get even more optimizations just by throwing GL and LTCG. And if this room holds to the statistics, about half of you are not throwing it. You should go do that. Okay? Now, and that creates a nicely optimized exe, more optimized than the one you got before. The last form of free optimization that we've always had is something called profile-guided optimization. Who knows profile-guided optimization? One. That's about the statistic that we have. About less than 10% of our customers know about profile-guided optimizations and use them. What are those? This is a different kind of optimization that you can still get from the compiler. What happens there is it's based on training scenarios. So as opposed to you just tell the compiler, hey, you try to analyze the code and understand it and figure out how it works, you're actually going to give the compiler some hints about how you use that code. How does the end user use that code? And based on those scenarios of how the user uses it, we will optimize. Okay? So how does it work? Can everybody see the thing at the bottom? I'll try to step out of the way. You get the same thing as LTCG, right? You have the CPPs, the OBJs, they're optimized into an optimized exe. Okay? After you do that, you have a nicely optimized exe that is as fast as the one you got with whole program optimization. You run it through training scenarios. Okay? You just go execute your app. Run it. If your app connects to a camera, gets a video, and then runs a certain algorithm on it, and then run it through a filter, and then you're done, just go through that scenario. Okay? And when you're done, run that compiler again on it with an option called LTCG PGO. So you run the compiler twice. And when that's finished, you get your exe again. Now even further optimized based on the scenario that you just ran it through. The easiest and fastest way to use LTCG, to use the PGO, is for startup. Many people want to make their app start faster. The simplest thing you can do is, after you build your binary, build it with PGI, run it through startup, close the application, optimize it again with PGO, and now you get faster startup. If you have specific scenarios that you care about the performance of, run it through those scenarios. If you're a video encoding application, for example, run it through those scenarios. The reason I try to talk about this one is that our data tells us less than 10% of our customers use it. But I can tell you that within Microsoft, everybody in Microsoft uses the Visual C++ compiler. And profile-guided optimizations is one of the hottest things that people in Windows, people in SQL, people in Office, people in Bing, people everywhere in Microsoft, they come to us and saying, make it better, we want this more, and we want that more. And people like SQL get more than 30% performance improvements over LTCG just by using PGO for the scenarios that they care about. Some people get 5%. Some people get 30+%. It varies, but you'll always get something. And the key thing about using PGO is don't run it, for example, through your tests, because you don't want it to optimize the edge cases. You don't want it to optimize the error conditions and all of these things. It will come at the expense of the real scenarios. So the hardest part is selecting what scenarios you care about. But you have specific scenarios for the application where performance is important. That's where you run it through PGI. And if you do that, you will actually get a pretty decent performance boost. So these were things that we had in the compiler. I want to say O2 forever, GL and LTCG we added maybe around 2003, I think. PGO we added in 2005. So most of you, who's using a compiler before 2003, Visual Studio 2003? One person, 2, 3, 4. Okay, we should talk. We should talk after the talk. Who's using 2005? 2008? 2010? 2012? Later? There's no later. Okay. All right. Well, let's say it's a good spread. Chances are, if you have 2005 and later, you already have all the things I've talked about here. You should go play with it and try it. If you don't have these, go get them, please. All right. In Visual Studio 2010, we went along that same road of let's add more optimizations that are free. Okay? So we looked at the hardware that we have, and hardware has evolved over the years. And one of the ways that hardware has evolved is the introduction of what's called vector registers and vector instructions. What are vector registers and vector instructions? The typical, x64, 64-bit hardware has every core has registers, R1 through R15 and REX and all of that. And then they also have another set of registers. And this other set of registers is wider registers. They're actually 4 times as wide as a normal register. And for these are called XMM1, XMM2, etc. And these, they already exist on your machines. Almost every machine that you have here, the laptop that you have, the desktop that you have, all of them have these registers now. And these have the capability of doing, say, 4 additions at a time or 4 multiplications at a time instead of 1 at a time. So let's say you had a loop that looks like this. You're going 1,000 times to the loop and adding an element from B and an element from C and putting it in the array A. Normally, you would execute that loop 1,000 times, executing 1,000 additions, right? With vectorizations, instead of doing R1 plus R2 and you put it in R3, we're going to load 4 of these in memory at the same time. So instead of doing 1 plus 1, 2, okay, 2 plus 2, 4, okay, 4 plus 4, 8, okay, and you do, load it at a time, 1 at a time. You load 1 and 2 and 3 and 4 and 1 and 2 and 3 and 4 and say, add them all at the same time. And then, add the first 4 elements, add the next 4 elements, add the next 4 elements. And so you can take that loop in just 250 iterations. on the same processor, right? And you're able to do that. And one of the things that we do now with Visual Studio 2010 is we do that for free. So if we detect that you have a loop that we can vectorize in this way, we will do it automatically for you. If we can detect that there is no loop carryover, for example, here it is not a sub I equals b sub I minus 1, because that totally kills that kind of optimization. Or if there's memory aliasing, like B and C share parts of the memory, or actually more A and B share parts of the memory. So an operation of A sub 1000 is affected by the impact of like A sub 5, then you can't do that kind of optimization. And the compiler is actually very smart about being able to detect these conditions. And it would vectorize that stuff. In fact, it's so smart that if you have these kinds of conditions in the loop, it can actually break the loop into two loops and optimize the first part that it can separate and leave the second part unoptimized. So it's actually pretty decent, pretty advanced, and that happens to you for free. You don't actually need to do anything. When you're throwing O2, now you're getting that kind of optimization with Visual Studio 2010. Did I say 2010? Visual Studio 2012. I'm sorry. The next kind of optimization that we do is called automatic parallelization. So for a while, we've been talking about one core, O2, whole program optimization, profile-guided optimization, auto-vectorization. All of these care about one core on your computer. All the other cores still unutilized. Now we'll start talking about these other cores. Most machines that you have now are quad-core. There are some dual-core, some more than that. Very few single-core remaining that you can buy at this point. So almost every machine, you're able to use more than just one CPU. So why is it that we're only using one CPU to optimize your application? Can't we do more than that? So that's what automatic parallelization does. Okay? Automatic parallelization takes that same kind of loop that we had, and instead of just using both the scalar and the vector unit on the one CPU, it will actually parallelize it on a number of CPUs that you have. You can tell us how many you wanted to just a hint of, this can be parallelized on 4, and we will do it for you. You don't need to worry about the creation of threads or any of that stuff. It's just a very quick, please go parallelize that for me. And we'll do some detections. If we can, we will. All right? So that's the other kind of free optimization that you can get. But this one, you need to give us a little bit of a hint. This loop can be parallelized. Please go do it. To be able to do that, you have to throw the /qpar compiler switch. So throw /qpar, do the pound pragma, and then you're able to get automatic parallelization in loops. So we talked about the things that you get for almost free, like either 100% free, or you do a little bit of hinting for us, show me a scenario or throw me a switch, and then I'll do the optimization for you. And let's talk about if you actually wanted to take things in your own hands. We're developers, C++ developers, hardworking, smart developers, tend to be the most up-to-date with, if anybody knows how to do parallelism, it's people who use C++, right? So how do we make it easier for you to get that last extra squeeze out of the CPU? What tools do we provide you to do that? So next section, I will start talking about that. The main thing I'll talk about is something we call the parallel patterns library. Anybody already using parallel patterns library? Couple, okay. Parallel patterns library is part of the C++ runtime, so you get it with every application starting Visual Studio 2010. It's already part of your application. You can use it, right? And what it provides you is the ability to work with threads at a higher abstraction level. So you don't actually need to think of them as threads, but you think of them as chunks of work that we call tasks. Okay? So think about tasks, and then allow that parallel patterns library to handle those tasks for you. So we have a scheduler in something called the concurrency runtime, and that scheduler knows how to, schedule the available cores the best way. We've invested a lot in how that scheduler works. And the key thing, if there's one thing you're going to remember here, is parallel patterns library, contrary to how you do it in normal threading, is You don't express the desired parallelism that you want. You express the potential parallelism that is possible. And then you leave it up to the runtime to actually do the most. So for example, you're going to say, I want to run these 4 tasks in parallel. What you're really saying is, these 4 tasks can be run in parallel. If you can do that, do it. If you find that it's more optimal to do something else, do that too. Okay? And what happens is the concurrency runtime can actually detect and say, oh, now I am running on a quad-core machine, but I'm in a battery optimization mode, and only 2 cores are really active at high speed, therefore I'll only use 2 cores. Or now I'm running on a tablet that only has a single core, and I will use the single core. Or now it's been deployed on a server that actually is 64 cores. You'll start using 64 cores, all the way up to 256 cores. It's all plumbed in within the concurrency runtime. So all you need to do is just use one programming model that expresses this concurrency at a higher level, and then you let the PPL take care of it for you. In addition to the tasks concept, there is an agents concept, which is think of it as message passing. So the ability to have a message passing interface, buffers, and buffers that act like a queue, or buffers that overwrite with the last one, or buffers that only the first one sticks, and different kinds of buffers. And you can deal with those. So 2 kinds of concurrency can actually be captured here. So how does, what are the different ways you can use the parallel patterns library? Parallel patterns library is a big library. I mean, I could spend 2 or 3 talks just talking about the parallel patterns library. So I'll give you the highlights of it here. But definitely there's a lot more to read if you want to go to MSDN, or if you want to reach me after the talk, we can chat more about it. This is the simplest thing to do. This is a loop that says that it has the potential of executing on 1,000 cores. Okay? Who has seen lambdas before? About half the room. Okay, for the other half, I should just explain it real quick. Lambdas are these 3 lines, starting this funny bracket, ending with that curly bracket. And what this says really is it's a nameless function, an anonymous function. Think of it as a function object or a functor, for example, would be an equivalent. So what you're trying to do here is say, this body of code, create a function out of it. I'm just writing it in line for simplicity, but I might as well have created it outside and put a function pointer here. It would have been the same. Okay? And the syntax for lambda looks weird, but there's a little trick that will make it very easy. You just use all the brackets on the keyboard. That's how it works. So you start with the square brackets, then the circle brackets, and then the curly brackets. And when you use all the brackets on the keyboard, you've finished your lambda. So this basically says what variables you want to capture from the outside scope. This has the parameters that are being passed to the lambda. And this is the actual body of the lambda. Okay? So here, we're saying include ppl.h. This is actually where all of PPL code is. I'm lazy, so I'll use the namespace concurrency. Otherwise, I'd have to do concurrency : parallel 4. Parallel 4 is the name of the function, and it takes the 3 parameters. The index from 0, less than 1,000, do this work. Do work of I. So this is the equivalent of for I equals 0, I less than 1,000, I plus plus, do that body. Okay, it's exactly the same. The only difference here is I said, if you had a machine with 1,000 cores, which you probably don't, if you had a machine with 1,000 cores, feel free to do this parallelization on 1,000 cores for me. If you only have 4, we will do it on 4. If you only have 2 available, we'll do it on 2. Okay, we'll do it on whatever is available for us. Okay, so think of it that way, right? This is roughly what happens with that loop. You write it this way, and we find that you have core 4s, 4 cores, and we get the first 250 on one, last 250 on another, and we chunk it that way. You're not guaranteed that it's going to be chunked this way. The first core might actually get 750 to 999. There's no specific order that we get it in. In fact, it might not even end up doing all 250. For example, sometimes you have a nice if statement inside your loop, and it says like, if certain condition, do this really small operation. otherwise do this really big operation. And then, core number 1 could end up being lucky and it gets all 250 very small operations, while core number 4 is stuck with the 250 really big operations. So it's a very unbalanced world. The parallel patterns library, the concurrency runtime, is actually smart enough to do the work stealing. When core number 1 is done, it wakes up and says like, hey, I'm finished. Who has some work for me? And then core number 4 would respond and say like, I'm not even halfway through. Can you take some of mine? And then core number 1 says, okay, well, give me 100. We'll take 100. We'll start working through those. Okay, we did all that for you. You didn't have to do anything here. We did all that cycle stealing, the work stealing, all of that. We do that for you. And you can control that behavior too, because you're a C++ developer. You might even need more control over that. So you can control that. So for example, one of the things that you can do is say, I don't want to continue all 250. Some applications, for example, you're doing search. In that loop, you are inspecting 1,000 frames of a video and looking for a certain picture or a certain face, and you're doing face detection on 1,000 frames. Okay? Once you find it, there's no need in inspecting the rest of the 1,000 frames. You were looking for one, you found it. You can go and say, I am done, cancel all the others, and then you terminate that way. So there's that kind of facility in it. But that ability to cancel and the ability to do work stealing adds some overhead, right? So while you're working on 4 cores, you won't get 4x parallelism. You get a little less than that. Almost nobody gets the linear parallelism anyway. But you can reduce some of that overhead if you wanted to with something called parallel 4 fixed. And parallel 4 fixed is sort of an advanced scenario. If you know that your loop is 100% balanced, you really want it to 250 on this one, 250 on this one, 250 on this one, and 250 on the last one, just tell us parallel 4 fixed. We're not going to attempt to do any stealing. We're not going to attempt to do any of that stuff. And you get just divided on 4 core evenly. So you can do that too if you want. Iterating on a regular loop over an index variable like an integer is one kind of iteration. But we're C++ developers. We like STL. Using STL? Half? Okay. STL has these really nice containers and algorithms and iterators. And we just borrowed from the for each, and we said parallel for each. It works exactly the same way as parallel 4 does, but with STL containers. So now you can iterate over a vector from its beginning to its end and do the same kind of work, right? And you get exactly the same guarantees. Of course, it works best with containers that have random access, like you can say vector sub 5, right? With the serial iteration of other containers, it works okay, but you don't get the same kinds of performance benefits that you get with random access iterators. The other thing I want to show is, in addition to parallel 4 and parallel 4 each, there's something called parallel invoke. Okay? And think of this as instead of having different looping as the way to work, you go and say, this is not about the loop. I just have tasks, and those tasks I want to invoke on multiple threads if possible. Okay, and you can just tell the concurrency runtime that you want that, and the way you tell it that is using parallel invoke. So you can, in this example here, for example, we're trying to double things. We're going to double an integer, double a double, and double that string. Okay, and we're going to say parallel invoke. Here's again a lambda. Okay, we're giving it basically 3 functions. Parallel invoke those 3 functions. The first function calls twice on the integer, the second one on the double, and the third one on the string. And this is a nice template function that basically returns t plus t. Right? So your expectation here is it should write twice 54, which is 108, twice 5.6, which is 11.2, and twice hello, which is hello, hello. Okay, that is what is going to be outputted here. So what parallel invoke does is invoke this, invoke that in parallel if possible, if they're available. If not, we will queue some. Maybe we'll invoke these two together and this one on its own or something. We'll do the most optimal. And then at the end, we wait. Here we wait for all of them to return. When that happens, you're ready to continue. So it's a very easy way of just firing some of the threads. Instead of handling thread creation and doing all these things, say, oh, just invoke these functions in parallel for me, please. It's just very easy, right? You don't always want to wait, right? Some of the benefits of go invoke this for me is you don't want to wait for it to finish. You actually want to go do some other stuff, right? So how do you do that? Well, there's the concept of a task. And a task is basically a chunk of work. A chunk of work that you want to be done asynchronously, off of the current line of thread that you have, right? And the way that you create this task is you go and say, oh, I'm sorry. The way that you create this task is you go and say, create task. Okay? And you give it either a function pointer or the chunk of code that you have. In my case here, I have a very simple task that returns an integer. Returns 42 all the time. And there, once you create the task, it's automatically invoked on its own thread. Okay? Now it's working somewhere else. The rest of the code is executing. We're not waiting for the task to finish. We just said you can go ahead and start whenever you can. This could be a long-running thing if you want to, right? And when you want to wait for it, you can do t.then, which is called a continuation. So t.then, so when this task is complete, invoke this function. And it takes as a parameter what this task returns. So now you expect the 42 that's returned here to be passed here. If I had a lot of code that is being executed in between, it would be running, and it would be running in parallel to while the task is executing. Right? So it's a very nice way of capturing that parallelism. Very, very, very simple to call. And the concept of continuations with t.then makes it very easy to be able to capture okay, when you're done, I want to be able to do this. And you can do t.then and then then. You can capture t.then that also returns another task and then wait for that and do .then. You can do as many .thens as you want. You can organize your code that way if you want. It's a very nice way of creating asynchronous programming. In fact, with Windows 8, there are a number of APIs that are all asynchronous. If you actually looked at Windows 8, for example, file creation APIs, file creation, there's no file open and then read and then close. There's file open async and read async. They're all asynchronous. You say, go read from the file, and the function is not going to return with how many bytes it read. The function just returns with a task. Tells you, here you go. Yeah, I started the file read operation. Do a .then when you want to. Okay? So it's a very nice way of dealing with asynchronous APIs that are now becoming part of Windows in Windows 8. To work, sort of couple the nice things like parallel for and parallel for each, we are giving you also parallel containers. And these are thread-safe and log-free containers. So actually, it's kind of the best form of concurrency that you can provide. So they're very, very, very fast containers. But to be able to get them to be that fast in the concurrent situations, we basically did remove some of the functionality. Okay? And we just left the kind of functionality that you would still want and you would still be able to get in a highly parallel environment. So think, for example, for vector. So we add a concurrent vector, a concurrent queue, a map, an unordered map, a set, all of that kind of stuff. And then what we also gave you, say, for example, in vector is vector, you can push back, okay? But you're not able to insert in the middle. Similarly, you can clear the vector completely, but you cannot erase a certain element or pop back just one last element, because these are things that we cannot do lock-free and concurrently very easily. Okay? So we provided you with some operations and said, these are the operations that if you want to use, we will do them very, very fast. You can put these in the body of a for loop, of a parallel for loop, and we were never blocked. There's not going to be somebody getting a critical section or something like that. It's going to be very fast in executing. But it has a limited set of operations. So if you're able to live within the constraints of those operations, you have some really fast data structures that you can access. And the interface for those data structures is exactly the same as STL. It's really modeled after STL. So if you're familiar with STL, you can actually use these very easily, and they mix and match with STL also very easily. And here's sort of an example of using a concurrent vector. Basically the same way that you use a normal vector. Vector of int, and then you do vector.pushback, and that works. Now you're executing this 5 million times, and you're doing those pushes concurrently with no locks at all. Very, very fast insertion. All right, so we talked about CPU. Any questions about the CPU before I start moving on to the other part of the hardware that we didn't talk about? Okay. So on almost every device that you have now, be it a desktop, a laptop, or even a tablet, okay, there is, in addition to the CPU with all its beautiful cores, most familiar configuration at this point is a quad core, we have a GPU, okay? And whereas a typical CPU would have 4 cores, GPUs typically have hundreds of cores. You're talking about a $100 graphics card on your machine. Very powerful, hundreds of cores available to you. They're very specific in terms of the kind of instructions that you can execute on them, but it can do massively parallel things. And unless your application was very heavy on graphics already and is doing a lot of things that have to do with displaying and a lot of processing while it's doing that, most people actually leave this highly idle while you're executing your code. In fact, one of the really nice things about the GPU is that from a power consumption perspective, it is actually better than a CPU. Okay? So this is actually, compared to a CPU, a low battery alternative. So why is it that when you're executing your application, we're only looking at the CPU but not GPU? So people lately have been looking at this and saying, you know, those GPU things, they can do things more than just displaying on a screen. They do a bunch of processing that maybe, just maybe, I can use. They're not valid for all kinds of processing, but for things that have to do with mathematics and like if you have a computation, a hard computation or something like that, they're really great at that. Now the challenge has been, even when you wanted to use the GPU, it was hard because, you know, on the CPU you have a range all the way from assembly to, you know, to scripting and everything in between. On the GPU, you have assembly and like almost assembly and maybe CUDA, which is like C with assembly. Like it's very hard. There was really no mainstream language that allows you to program the GPU. And even if there was, it's different from the language that you use for your CPU with a different compiler and different everything. So one of the things that we added to Visual Studio is the ability to target this GPU directly from your C++ code. So now you can go and say, for my algorithm, this algorithm, I would like this one on the GPU, please. And I'll show you how to do that. So we created something that we called C++ AMP. Anybody heard or used C++ AMP? A couple, okay. So C++ AMP, AMP first stands for Accelerated Massive Parallelism, and whoever coined that term needs some interesting, is definitely not a typical Microsoft term. So Accelerated Massive Parallelism is basically the way that we target GPUs using C++. It's actually not just for GPUs, it's for any kind of heterogeneous computing. And GPUs just tend to be a first example that we took for heterogeneous computing access. What does it provide you? Well, number one is it provides you with a nice programming model for expressing parallelism, data parallelism in specific. If you have a certain algorithm that deals with a lot of data, and that kind of data can be executed on in parallel, like for example, you know, scrubbing video frames, you can do that in parallel. Okay? Then it provides you with a nice programming model for that. That programming model is portable. Okay? We try to make it in a way that you can use across the different kinds of devices. Portability for us means, you know, it's not only going to work on an NVIDIA GPU, but not, for example, an ATI or AMD GPU or something. It'll work in any kind of GPU that you have. We even made it an open specification, so any other compiler can go and implement it too. It is not locked to Microsoft. In fact, Intel already has a prototype, Chevron Park, that makes it work on the Intel compiler using OpenCL, nothing to do with Microsoft at all, basically. And it allows you to get that performance, the very high performance that you can get from a GPU, without impacting your productivity as a C++ developer. Okay? So what do you get? You get that simple programming model that we talked about. You get the ability to run all the different kinds of hardware. You get the maximum performance for the kinds of scenarios that are possible to do data parallelism on. And the main thing here is you just use it for algorithms that are data parallel. This is not to be used for any kind of code that you have. So what's an example of that? Who can recognize what this program does? This is normal C++ code. Anybody recognizes what it does? You can't say, Mark. You know. Uh-huh. Hello World. That's right. This is a Hello World program. Okay, you're going to iterate over an array. It has Hello World -1, and you're just adding 1 to each and printing it. Okay, so this prints Hello World. It's a complicated way of playing Hello World, but it's a way that can be done in parallel, right? This loop. There's no reason that you need to do this loop serially. There's nothing in calculating that this is an H and this is an E that's dependent on each other. The memory is not shared in any way. This can be parallelized if you want to. In fact, this can be parallelized in the GPU if you want to. Not that this is going to be worth it, but it's a good example for how you can take something as simple as this and make it go on the GPU. So how do you do that? If you wanted to run this on the GPU, how would you do it? With AMP. First, you would include amp.h. This gives you access to the AMP library and compiler features. And you would, I'm lazy, I like to do using namespace concurrency, so I don't have to do concurrency : whatever I'm going to use next, okay? So amp.h, that's all you need to remember. And then what happens after that? You use something called array view, okay? An array view is just a view on top of an array stored somewhere else. In this case, it's going to be an array on top of a view on top of this array, of the array v. And we already said its length is 11, and it has ints inside it, okay? And array view is a very smart data structure. It's a data structure that knows that, oh, I can run this kind of thing on the GPU, and it's very smart about when it's going to copy stuff. So it's not, here you're not doing a copy of everything from here there. You're not doing that. It's just saying that at some point in time, I might be interested in getting the contents of V. Okay, bear that in mind, compiler. So it's more of it's a tricky data type. It's not all expressed in a library code. There's parts of it that there are compiler smarts about this data type. Okay, and instead of having the V, instead of using V inside the loop, I will use the array view. Okay, simple so far. And instead of printing V, I'll print AV. So basically, consider AV to be an alias to V in some way. And now I'm just using AV everywhere. And I will replace the 4 with a parallel for each, the same one that we used in PPL, right? And it's going to say, I'm going to iterate over the extent of AV. It has a member extent that basically says, I have all these 11 items, and execute that lambda. Okay, it takes a parameter IDX, and now you can use that IDX inside the lambda. Okay? And I added restrict amp. That's where all the magic happens, this restrict amp. What restrict amp does is it says this code that is coming as part of this function, in our case it's a lambda, but it could be any function. We're saying this code, please compile it for the GPU, not the CPU. Okay? Create GPU code for that. And when it's executing live, execute it on the GPU. So now, when you're stepping through this program, here, all CPU, here you said, array view, still doing some stuff on the CPU. Parallel for each itself, the iteration is happening on the CPU. But this one, every time you're calling the body of the method here for each, we're automatically doing the go do some stuff on the GPU and get the result back. Okay? And when you're done, all of this is running again on the CPU. So you did the hard part of iteration and loop, and you can imagine if this was a complex one, and I'll show you a demo of the more complex thing, all happening on the GPU. Okay? And AV, the nice smart about it is it only starts copying the data that is needed on demand on the GPU. So if you don't need the whole data, we won't copy the whole data. If you never use it inside, we don't copy it. If there was an if statement and it never reaches the part where AV is used, we will never copy it. So we'll be very, very smart about what we copy to the GPU. Why? Because copying to the GPU is an expensive operation. In fact, if you actually executed this program, it probably runs slower on the GPU than it runs on the CPU. Why? Because this is a trivial operation on the CPU. You don't take that to the GPU and copy it and start invoking all that other stuff. One thing I did not say about this is the way that actually this works behind the scenes is by using DirectX. As part of the compilation here, we generate code that's called HLSL code. And that HLSL bytecode at runtime gets generated into code that runs on the GPU, shader that runs on the GPU. But this is all behind the scenes. And I explicitly did not want to say that before, up front, so you don't think it's like, oh, this is some DirectX thing. This is just an implementation that we chose today. We could change that implementation tomorrow if you wanted to, right? But for you, this is how we're giving you the ability to be able to run on any graphics card that Windows supports. In fact, you can if you had two GPUs, one from AMD and one from NVIDIA, we would parallelize stuff on both of them at the same time, and we don't care because we use a very cross-vendor way. I will not spend a lot of time on the debugging tools that we get you, but just so you know, we have a full set of debugging tools for how to do parallel and GPU debugging. So in addition to the normal stack window that you have, the call stack that you have, and the watch and all of this, we have a parallel call stack that shows you how many threads are stuck in a specific place, or a parallel watch that says you what's the value of this specific variable across the multiple threads, so you don't have to see 256 instances of that variable. So things like that. We also allow you to step through the GPU code if you want. So that parallel 4 that's actually executing on the GPU, you could go and step through it if you wanted to. We also, of course, provide you with nice printf debugging too, if you want that. Some people like that. And this is a picture of what it looks like. So the last thing I'll show you is just a quick demo of how this all comes together. The single core, the multi-core, and using the GPU. Okay? Now let's see if I can do the same trick of showing you my desktop. Yes, good. Let's go back to Visual Studio, my favorite program in the world. So this is an application that we created in our team, called it Cartoonizer. And what Cartoonizer does is it grabs the feed from the webcam that's associated with the computer, and it does some filter on it that makes whatever it's capturing look like a cartoon thingy, and plays it live on the screen. So here's what you get if you were doing it on a single core. Is this showing? See how jittery it is? It's not fast, and I can do some karate. It's kind of very choppy, right? This is because you're trying to do a very heavy data-based algorithm, very heavy computations on just one CPU. And even though we actually do this vectorized, it's just not enough. I can even hear the fan on my machine now starting work. You're really trying to kill that CPU. Nothing is happening. So let's see what you can get if you did multi-core. Sorry. That is always bound to happen in any live demo. So this is only to show you that it's a real code. All right. So let me do the same thing on a multi-core. And let's start it. Okay. You'll see it's a little bit less choppy. Still not 100% fluid. But you get some better. And the way we did this multi-core is using PPL. So I'll show you the code in a minute. Now I can go to C++ AMP and see what that looks like. See? A lot faster than the multi-core. And actually, it's a lot faster on my machine than it is on the projector. Okay? And this is just basically almost as fast as without a filter on it. Okay? And this is done using AMP. It's the same algorithm. So let me show you the code and what it looks like. Okay? This is the part of the code that actually does, on a single frame, try to cartoonize that frame. Okay? And executes a certain algorithm on it. It gets the pixels in RGBs, tries to populate their values in a frame view. So it goes in a doubly nested loop here and tries to do some computation. Okay? And then it applies color simplification on it in another doubly nested loop. Okay? It's a very simple algorithm that is executed. And because we're doing it on a multi-core, and even though we can potentially parallelize some of that or vectorize some of that, you still don't get all what you can get out of vectorizing on multiple CPUs. So let's look at the next one, which does it on multiple CPUs. It's exactly the same, except instead of doing a doubly nested for loop here, the first one I just parallelized with parallel for. Everything else is exactly the same. Okay, I just did replace the for loop with parallel for. The computation is the same, even the inner loop is the same. I didn't need to parallelize the inner loop because I get enough work by parallelizing the outer loop. So there's no need to create more work to be parallelized if I can get full parallelization. And it does all the stealing within the different ones. If one frame takes longer than the other, they will steal. And I do the same thing for the color simplification. So the loop for color simplification, this one I parallelize the interior loop, and that works well as well. So that's really all I did. Replace a for loop with a parallel for, and pound include ppl.h. There you go, very easy. Now how did I go about AMP? Well, it's almost the same, except that now I put stuff in those arrays, similar to the array views that we talked about, right? And now I have an array view that goes over my type, right? And then I do a parallel for each with, let me move this up a little bit so you can see it, everybody. This line here. Oh. I'm sorry. Let's go back. Okay. This line here. Get the mouse out of the way. And it says restrict AMP. Okay. Same parallel for each, but now iterating over that array view, and I do restrict AMP on it. Now it executes it on the GPU. Okay. Same algorithm. It really wasn't hard to take that algorithm and make it run through AMP. And the same thing I do on the color simplification phase. So it's a two-phase algorithm. Okay. Same thing. I do that restrict AMP, and it runs on the GPU. And the actual implementation of the algorithm itself is actually pretty straightforward C++ code. Floats and ints and a struct and do some math on it. And it's the same for all of them. Okay? And that basically took my application from being very, very choppy to, a little bit smoother, but still not great, to extremely smooth. This is specifically, what we call, a almost embarrassingly parallel algorithm. Embarrassingly in a good way. It's a very parallel algorithm, and it's something that can be executed on multiple cores and can be executed, in this case, on hundreds of cores on a GPU. And this laptop that I have here is not like a very fancy laptop with a big GPU. It's actually one of those really thin laptops with an Intel-based GPU. Still does a very good job. And the nice thing about it is, even if you don't have a very big GPU, AMP can just scale down all the way to running on CPU only. If you compile something with restrict AMP and you try to run it on a computer that doesn't have a big GPU, it will still work on, say, Surface on your Surface RT or the Surface Pro. Surface Pro actually has a nice thing. It works very well. But the Surface RT, we execute on, because we use DirectX, we execute on something called Warp. And that does the GPU emulation on a CPU. And you still get actually a nice speed up because you do get vectorization and things like that. So you can just use AMP, and it will run everywhere where DX11 is supported. Okay? All right. So this is just a quick summary, right? Showed you how to do the fast stuff, the things that you get for free. So you're ready, probably throw O2. If you're not throwing GL and LTCG, go do that. And go play with PGO. It's not that hard to use. And it can get you significant gains. Parallel patterns library, a very interesting one to read about. Just express your parallelism that way. And it can coexist with all the other threads and all the stuff that you can create, so you don't have to move your whole application that way, but start creating new things that way. And last, if you have algorithms that can actually benefit from data parallelism, go start looking at AMP. It's a very good way of getting that done, offloaded to the GPU. And with that, I'll open it up to questions, if you have any questions for me. Yes? Yeah. So the question is, in the free optimization where you run it through training scenarios, so profile guided optimization, can you automate that process of running your scenarios? Yes, you can. So the way that you do it is when you create, when we first instrument the application, when you compile it the first time, it is built such that when it executes, it creates count files next to the binaries that are created. So you can have, if you have like a nightly build script or something that executes every night, or a continuous build that executes, you can, if you have a way of running these scenarios through it, if you have an automated, we don't provide you with an automated way of running the scenarios. But if you know, if you have an automated script already, and you know how to plug in those scenarios into the script, all you need to do is take the count files that are then emitted next to the XZN binary, and move them in the right space for the compiler to find them. So on the machine where it's going to be linked. And then when you link again, they will actually be used. So you can do that. But you'll have to do it manually yourself. You set it up manually, and then it can run every night after that. The other thing is you don't actually need to run it for every build. We can do some smart things about how much to reuse of existing counts that we have. Because when you change, say, you change one function, it doesn't even necessarily change the areas where we optimized or the areas where we collected the most counts. So we can tell you when your counts are starting to get out of date. So you can train once and optimize a number of times, build a number of times before you have to train it again. And then just test for how stale the data is. It's a good question. Thanks. Very good question. So the question was, you mentioned Windows 8, and that these are optimizations for your Windows 8 applications. Does that mean that they're not going to work on Windows 7 or something? No, absolutely not. This is for Windows 8 and for, would also work on Windows 7 applications. We did some extra work to make sure that it works very well in Windows 8 applications, but it has always worked fine on Windows 7 applications as well. So you could use the same techniques, whether the free ones or PPL or AMP, and it would work equally well on Windows 8 desktop applications or Windows 7 desktop applications for as well. AMP, for example, is not available all the way down to XP. So if you have an XP app, you can't use AMP on it. It has to be Windows 7 Plus. So there are restrictions on each one of these and how down level you can actually go with it. Correct. It's because of the DirectX 11 requirement, and XP doesn't have that. That's right. But that's a good question as well. All right. Well, thank you very much. Thanks for coming. I appreciate it.